Hello everyone, welcome to Atoms and Sporks, and in this video I want to talk about that so mysterious thing called quantum tunneling. Now in previous videos on this channel, we've tackled similar topics. We've talked about how quantum tunneling is derailing computing technology, for example. We also more generally talked about the applications of quantum physics and technology, but in this video I want to get more specific. What I want to do is to take this aspect of quantum physics that is so often represented in popular science stuff as something that is just absolutely crazy, seemingly impossible, and kind of take it off that pedestal. I want to get us to understand that it's actually not as strange as all that, and really it's just something that waves in general do. And then I want to go further and take some time to see how we've actually been using this quantum tunneling effect for decades and decades to make a number of technologies that we see in our everyday life. So it's neither arcane and impossible to understand, nor academic and of no benefit to everyday life. To make this point, I've chosen 3 technologies specifically that involve application from everywhere, from computers to cars to washing machines and even broadcast television. Literally all over technology. And those techs I've chosen are flash memory, which is the main computer memory in things like thumb drives and also smartphones and a lot of computers, as well as 2 types of what are called diodes, Zener diodes and tunnel diodes, which are used in all kinds of electronics and radio technology. But before we get into that, let's talk about what quantum tunneling actually is. Well, if you've never heard of it before, and you reached for a typical popular science book, they probably tell you it's when a particle like an electron can sort of like magically teleport through some sort of barrier. They'll maybe bring up Star Trek, throw up some crazy CGI, and see that because of this tunneling, electrons can move through solid objects, and it's all due to the impossible, mysterious laws of quantum physics. Except that really isn't the case. Quantum tunneling is actually just something that waves do, that all waves do. Ocean waves, sound waves, light, they can all tunnel. It's just called something different. With those waves, they call it either evanescent wave coupling or near field coupling. So the jargon might be different, but tunneling is just the same regular wave property in a new context. You see, as it often comes up on this channel, if I were forced to describe quantum physics in one sentence, it'd be that particles like electrons aren't little billiard balls, but wave-like things that have therefore regular wave-like properties. That admittedly is very strange, that something like an electron is kinda a wave. But once we accept that, the fact that such waves should tunnel is not anything that is additionally any more mysterious. It's just this regular wave-like behavior, this evanescent coupling business. Okay, but then what is this evanescent coupling business? I mean, I'd forgive you if you've never heard of it before. Well, in order to understand evanescent coupling, we first have to understand what are called evanescent fields. And evanescent fields are something that happen when a wave hits some boundary, and that boundary perfectly reflects it so that none of it actually transmits through the boundary. Now, when this happens, you might think that if I looked inside the boundary, I'd see no waviness or disturbance at all, since we know there's definitely no wave propagating through there. However, that's not actually the case. If the wave did abruptly end at the boundary, that would lead to a kink in a wave, and that is something that waves really don't like. There are some fairly abstract reasons for this. For example, it implies a violation of conservation of energy and momentum. But the point is, oscillating phenomena don't allow kinks or discontinuities. It's just a big no-no for them. So if no wave can propagate through the boundary, but it still can't just abruptly end, then what does it do? Well, it sets up a so-called evanescent field. It kind of leaks a bit, or continuously dies out into the boundary region. It doesn't propagate, but it's still there. And it is this evanescent field that is at the heart of quantum tunneling. Because the thing is, look what happens if I have this perfectly reflecting layer, but I make the layer very physically thin. Well, because of the evanescent field, the wave isn't actually completely dead by the time it reaches the other side when the layer is thin. And if that's the case, the part of the wave that survives this exponential decay and manages to make it to freedom on the other side, well, it can actually just keep trucking. This is called evanescent coupling. In a nutshell, if I have a thick, perfect reflecting material, a wave doesn't abruptly end at its interface. Instead, it leaks in a bit, even if it doesn't propagate. However, if I make that material thinner and thinner, it's actually possible for some of the wave to survive this decay before hitting a region where it can, freely propagate again. Thus, the reflected wave will decrease in intensity, and suddenly there will be a transmitted wave, even though the material is technically a perfect reflector of the wave. And that's all quantum tunneling is. It's electron waves evanescently transmitting through a thin layer of insulating material. There's really no additional mystery there once we accept that electrons are these wavy things. But then, in what real situations does this evanescent coupling actually happen to regular waves? Well, it's maybe not the most common example, but a particularly illuminating case is reflections in a narrowing waveguide. But what's a waveguide? Well, a waveguide is kind of like a transmission line for waves. It helps them propagate from one place to another without any losses in between. There are radio waveguides that transmit radio light from, say, an antenna to a transmitter. There are microwave waveguides, like those that transmit microwaves from the magnetron to the cooking chamber in a microwave oven. There are visible waveguides, like fiber optic cables. Hell, even the rubber tube of a doctor's stethoscope can be considered to be an acoustic waveguide. So waveguides are a very common technology, and a basic property of waveguides is that because they're only so wide that only certain so-called transverse modes can exist within them. By transverse, we mean the direction perpendicular to the way the wave is moving, and in this direction things are much like a guitar string. The edges of the guide clamp down the wave, and so only certain notes or modes can fit. However, although things are discrete or quantized in the transverse direction, for all intents and purposes in the longitudinal direction, which is the direction of propagation, really any wave can fit. So the transverse direction can only transmit discrete transverse modes, but the longitudinal direction can accept a continuum of modes. When you put these two facts together, we find that each of these transverse modes acts like a base or foundation for a continuous range of allowed frequencies called bands that the waveguide can transmit. Frequencies below the bottom of the edge of these bands, however, won't transmit and can't exist in the guide because they would require the transverse direction to take a shape that wouldn't fit the boundary. So hopefully that makes sense, and thus, given that waveguides have these bands with lower cutoffs, and the fact that these cutoffs depend on the width of the guide, then what happens when you connect two waveguides where one is thinner than the other? Well, because the widths are different, it's then possible that a mode that is transmitting in a given band of the larger waveguide is going to be below the cutoff for the second smaller waveguide. For such a mode, what happens? Well, it's perfectly reflected at the interface between the two waveguides, and you get no transmission. Nothing comes out the other end with that frequency. That is, unless the second waveguide section is actually quite short. Because as we've learned, there will still be an evanescent field in the second waveguide, and so if it's very short, the mode can evanescently couple, and the wave can still partially transmit. And, by the way, this is not just like some bizarre artificial situation. This real physical effect of having our transmitted wave being attenuated or less intense because of this small region where the wave goes evanescent is actually how something called waveguide attenuators actually work. These are things that you put in real waveguide circuits when you want to step down the intensity of the wave for some reason. They work by basically putting an evanescent thinned region and thus producing a transmitted wave of reduced intensity. So we use this effect in real technology. So this is something that happens in waveguides for light, waveguides for sound, and so on, and in that context we call it evanescent coupling. But it's also something that can happen to electrons in a solid, where we call it quantum tunneling. The most common situation where you'll find electron tunneling is when you have a certain sequence of thin layers of different materials. In fact, a specific sequence that we really want to look at is when you have a thin layer of insulating material that is separating or dividing two regions of a more conductive material. In real technologies, the conductive material we're talking about is usually a semiconductor, more specifically it's usually silicon, and then the insulator is then actually often just silicon dioxide, which is basically what glass or quartz is. The reason you so often find this particular combination is because from a manufacturing perspective, all you need to do to convert silicon, which is a semiconductor, into a thin layer of silicon dioxide, which is an insulator, is just to heat it in the presence of oxygen. Silicon dioxide is basically just silicon rust. It's just oxidized. So these two make for an easy to make combination. But anyways, so why does this situation result in quantum tunneling? Well, in a solid, electrons can only hold certain states, which we've talked about already in a previous video. Specifically, if we were to look at how many states exist in a material for an electron at a given energy, in solids we would find continuous clusters of states, called bands, that are separated by so-called band gaps, which are ranges of energy where there exist no valid states in the material with that energy. Electrons with that energy simply can't exist in the solid. Given this, we see that something very interesting happens when we look at our semiconductor-insulator-semiconductor situation, because by definition what makes an insulator an insulator is that it has a very large band gap, much larger than a semiconductor. Thus we see that in this arrangement, if we look at electrons in these states here, which for reasons we'll leave for another video are the most important electrons, you have a situation very similar to our narrowing waveguide. Electrons in these states, in these semiconductors, are going to perfectly reflect off the insulator because there are no states in the insulator with that energy. If they can't exist, then they reflect. Except, as we now understand, that doesn't mean that the concentration of electrons with that energy will actually abruptly become zero as we move into the insulating layer. No, our electrons are wavy things, and therefore in a situation like this, they will set up an evanescent field that leaks into the insulator. And if the insulator is physically very thin, then you can actually have a detectable electrical tunneling current conduct by electrons in these states, even though there were no states for them in the middle layer. Okay, so let's say we understand that. Then how can this tunneling current be used to make a useful technology? Well, because in a situation like this, we can actually turn this flow on and off at will just by applying an electrical voltage, like from a battery or a power source. But how? Well, when we say we're applying an electrical voltage to something, what it really means is that we're changing the potential energy of the states of one side of the system relative to the other side of the system. This also, by the way, has an effect within the insulator layer as well. Basically, one side of the insulator will then be lower in energy than the other, and that's our kind of rectangular in energy range of evanescent states is now more triangular, which means that electrons at many energies have less distance they have to evanescently leak through, so effectively the barrier to evanescent transmission is smaller. In fact, we'll actually return to our first ramification where the two semiconductors have shifted energies in a second, but this simple fact alone, the fact that the tunneling barrier of the insulator reduces with voltage, is all we need to understand our first technology, flash memory. But what is flash memory? Flash memory is the computer memory in your smartphone. It's the memory in a thumb drive, and chances are it's the memory in your computer or laptop. And whenever you make a memory, you need a way to store a single binary state, a 0 or a 1. That's what allows you to store digital information. Now, before flash memory, there were magnetic hard drives, and in those, this was done by having a bunch of little magnetic regions where the magnetic state could be flipped from opposite polarizations to give your bit. But magnetic hard drives are slow, since they literally require a physical magnetic disk to spin, and thus also clearly have physical moving parts, which makes them a very bad idea for something that's getting bumped around all the time like a smartphone. So in came flash memory. Now, in flash memory, the 0 or 1 state is encoded in the charge state of what is called a floating gate. Basically, you have a teeny metal layer that can hold electrons that is completely encased in insulating material. So it's completely isolated and insulated, and like not hooked up to any wires or electrical contacts, and any electrons that are on there are trapped. And whether there are or aren't electrons on that floating gate is something that can then be detected remotely by the effect of those charges and their electric field, and so we can read our little bit. And that's what gives us our memory. If you turn the device off, the electrons are still trapped and they stay there, so when you turn your device back on later, your information is still stored. But, I mean, given that, a very immediate question you might have is, if this floating gate is completely insulated from any wires or contacts, how do you even get electrons onto it or off of it in the first place? Well, through quantum tunneling. You see, this floating metal island is separated from a great reservoir of electrons by a thin layer of insulating material. Now, this insulating layer is thin, but it's still thick enough that quantum tunneling is quite limited at equilibrium. Limited, though it's important to point out that tunneling still does happen at equilibrium, just very slowly. In fact, flash memory manufacturers generally guarantee that tunneling will be slow enough when the device is off that a detectable number of electrons will remain for at least 10 years, but no longer. They only guarantee the charge state will last for like a decade. So by the way, don't use flash memory for like long-term storage, by the way. Your data will be gone. So, if we do nothing, electrons that are on there stay there for at least 10 years. But if we then apply a voltage to this sequence of layers, as we discussed, this insulating layer separating the island and the reservoir of charges gets more triangular, and thus effectively thinner, and tunneling current increases exponentially. And suddenly tons of electrons can flow onto or off of the island. And that's how flash memory works, through quantum tunneling onto and off of an insulating metal islands. Or at least that is a very crude, brief overview. If you'd like to know more about this, like for example why we use quantum tunneling versus other ways, I provided a link in the description to a blog post I made where I give some more detail. But anyways, moving on, we said that when we have a sequence of layers like this with a thin insulating layer, and we apply a voltage to it, in addition to the insulating layer potential barrier getting thinner, that the energy of the states of one side are lowered relative to the other side. Given that, let's say you had a different material at the opposite side of the insulator. Both semiconductors, but say that the semiconductor on the other side, for whatever reason, was different so that it naturally had states like this. We see that for our important electrons here, flow is now impossible, because not only are there no states for them in the insulator, which was the case before, but now there aren't any for them in the semiconductor on the other side either. So then what happens if I apply voltage to this system so that I shift their states even more apart like this? Well, at first that might seem like a terrible idea, looks like it's making things worse and worse. Except, look what happens once you hit a very specific critical voltage. Suddenly there opens up a path for electron flow via tunneling of electrons from this band through the thin insulating layer into this band. We say that a tunneling window has opened. Because of this, if you were to plot the current that flows through such a device versus voltage, it would initially be very small, meaning it's acting like a resistor and it's blocking the flow of electricity. And that would continue as our voltage gets higher and higher until, at some very specific critical voltage, this tunneling window opens up and it becomes extremely conductive. This effect is called Zener breakdown, and although breakdown sounds like a bad word, it's actually something we can use to make something called a Zener diode. Never heard of a Zener diode? Well, unless you're an electrical engineer, I wouldn't blame you, but they're typically used like a kind of teeny tiny release valve in electrical circuits. If you have a circuit and the input voltage to that circuit is behaving normally and is low, then a Zener diode does nothing because it's below this critical voltage, so it's very resistive and the electricity kind of just flows around it. But if the voltage in the circuit should suddenly spike or surge for some reason and go much higher than it should, then suddenly you're going to exceed this critical voltage, and basically flow will be diverted through the Zener. And this ensures that the higher voltage doesn't get communicated to the rest of the circuit, which would be bad. And these are the kind of things that Zener diodes are used for. You might find them in, for example, PC power supplies, or on the side of your computer you have things like USB ports. While there may be Zener diodes there to protect against shorts and surges, you'll also find them in simple circuits that control basic appliances like crockpots, coffee makers, maybe like dishwashers and laundry machines. They'll also be in many automotive circuits like in your car's electronics, really all kinds of places. And that's all made possible by the quantum tunneling of electrons through this tunneling window, and the fact that this critical voltage can be engineered by controlling material properties. And actually, if we understand how these Zener diodes are working, we can almost pretty much immediately understand how another type of diode works, what is called a tunnel or Esaki diode. Leo Esaki, by the way, won the Nobel Prize in Physics for these in 1973. These diodes are just like Zener diodes, just with one small difference. In a tunnel diode, the materials that make up our little 3-layer sequence are engineered such that the default state, where no voltage is applied, is for the tunneling window to be open, where in Zener diodes the default was that it was closed. Because of this, tunnel diodes exhibit what is called negative differential resistance. In a nutshell, the natural state of things in electronics is that as you apply more and more voltage to something, you will get a higher and higher flow of electrical current. Current and voltage increase together. But in tunnel diodes, things get a little wonky. Initially, when you apply a voltage, this is true, because the tunneling window is open. But at a certain voltage, it will then start to close, and thus current will actually decrease even though you're still increasing the voltage. So it's like the resistance is turning negative. The increasing voltage causes a decrease in current, and it's this negative resistance and this hump that makes tunnel diodes useful. In a nutshell, without getting into too much detail, devices that have this hump like this can do special things when you have an oscillating voltage. And by oscillating voltage, we generally mean like a radio signal. Devices like this, with this hump, can be used to build circuits, for example, that create radio signals, or process radio signals, or amplify radio signals. And I know that's vague, but hopefully that's enough to maybe get an idea of why historically these tunnel diodes were used in a lot of circuits involved in things like TV tuners and satellite TV. I say historically because over the decades they've actually kind of fallen out of favor, since there are now actually better options on the market, but there was a time at least where these were big technology, and they only work because of quantum tunneling. And with all that said, let's maybe wrap things up. In this video, we learned what quantum tunneling is. It's electron waves doing a regular wave thing, what's called evanescent coupling. We also learned that there is nothing academic or theoretical about this tunneling, and that it is an important aspect of many modern technologies. Specifically, we looked at flash memory, Zener diodes, and tunneling diodes. And even though there are some more quantum tunneling technologies out there, with just those three, we saw direct applications to huge swaths of modern life, ranging from computer memory and computer circuits to household appliances and broadcast television. So hopefully that is enough to make the point which we so often make on this channel, which is that quantum physics isn't locked in the ivory tower. It's not useless, and in fact it always has been and will continue to be one of the biggest drivers of the modern age. So I hope you enjoyed this video. If you did, maybe like and subscribe, and have a good one.